And with that, I am really excited to announce our next speaker. Our next speaker is the co-founder and chief technologist at Databricks, here to talk about LLMOps, making LLM applications production grade. Please welcome Matei Zaharia. Hi, Matei.
Thanks for having me here.
Of course, thank you for joining us again this year. Over to you.
Always, yeah. So let me just put up my slides here. Great, yeah. So I'm going to talk about this sort of emerging area of LLMOps, how to make LLM applications really production grade. And I'll talk about it from a few different angles. So we're actually building a lot of internal LLM applications at Databricks, helping a lot of customers with them. So we're doing a bunch of stuff there that we've learned along the way and trying to create basically open source frameworks to support some of these. And I've also been doing some research at Stanford on kind of more powerful programming models for LLM applications. And I'll tell you a little bit about that as well. So hopefully you'll see some research stuff too. So obviously, large language models are really amazing. They're very great at synthesizing, text that, does a particular thing you want, fits well in context, and in general is a very useful building block. So, all the way back from the, original, like what today we'd call small, smaller language models that were able to do few-shot learning, to things like ChatGPT, where you can ask them questions and, they'll answer them, they'll correct code for you, and they'll do all this stuff. You get really powerful capabilities. But if you double click on these and look a little bit more at the outputs of these models, you'll find that they often have problems. So for example, if you ask ChatGPT when Stanford University was founded, it would say 1891. But actually, that's not true. It actually just opened to students in 1891, but it was founded a few years earlier. So it's like the wrong date. If you asked about this Colbert model, which is something developed in my group, we were very excited to ask it about this. And of course, it kind of knew what Colbert is, but it got it wrong. It said it was developed at Salesforce, which had nothing to do with it. And even if you ask it stuff about code, it will give you an answer. And I guess you can't see all the code here, but in this case, it says to parallelize the code, you should use thread pool executor, which is true in Python, you should, but the problem in the code was like, it's a serial algorithm that will crash if you just try to do it in parallel. You need to change the algorithm. So obviously, there are a lot of challenges in getting quality from these. And then even if you solve these, and there's various techniques, there are many operational challenges with LLMs. There's just the cost of running them, the potential for them to go down, whether you're serving your own model or running it on a provider. There are changes in the models over time. There's this idea of prompt drift that people have been talking about, where like if you ask one of these commercial models a certain thing, over time it will actually change its answer, and maybe you have to change your prompts to get it to do something. And then also you may need to update these models very frequently to keep up to date with knowledge, right? Like these famously have very old knowledge that's out of date, or to implement things like privacy. Like I have this example here where you can ask it about people, and at least about famous people, ChatGPT will give you an answer. But if Bill Gates was European, he could ask OpenAI to like remove this data about him, and they'd have to remove it from the model under GDPR. So that's many things you have to do to actually operationalize an app depending on your domain. So how can we make these apps reliable? So this is kind of this area of LLMOps. And I'll talk about three different things. I'll talk about just kind of extending standard MLOps practices to generative AI, and some of the work we've been doing in the MLflow open source framework based on what we learned is important. I'll talk about this new programming model we're building, which is related to chaining and agents and so on, but tries to automatically optimize your application for you. That's called DSP. And I'll also talk about some other techniques. Okay, so you're setting out to build your LLM application. How do you make sure this will happen reliably? I always say you should start with the basics. It's still some kind of machine learning application, and there are things that we've been doing for decades in machine learning that matter a lot. Not least of which is data, of course. That's why everyone's at this conference today. But in addition to really solid data, you probably need a way to be able to compare different models or different algorithms. So have a way to swap and compare language models and pipelines for your app, and be able to iterate on them and see which one does better. That's one thing you need. You need a way to track and evaluate outputs. This is a little bit harder for generative models that produce a lot of text, because your output isn't just like a number, and evaluation, it's not just like accuracy, like something you can easily compute. You have to figure out, is this paragraph of text better than that paragraph of text? So it needs to look a little different. You also need a way to deploy the pipelines in many places and be able to run them and at scale. And of course, you need a way to monitor these apps. So we at Databricks, we had developed this open source framework, MLflow, for MLOps with very large community, and we're actually adding a lot of these there, and also integrating some of the best-in-class tools that are emerging for language models. So you can have a great basis for starting your ML project. So just to give you a sense of a couple of the things that we're doing, the first one is an abstraction layer over language models, and in fact over things like pipelines as well, that lets you easily swap and compare these in an application. And we found that this is essential for rapid iteration. We actually have a lot of internal teams building various product features with language models, and they all want to be able to say, compare different providers, compare different prompts, compare different pipelines. Some of them use a multi-step pipeline, swap in their own model once if they want to train their own model for a specific task. So you need this abstraction. Now, in MLflow, if you haven't used that, there's already an abstraction for a model that basically wraps an arbitrary function. And there's a lot of stuff built around it. Like there's a general evaluation framework that can take any model and compute various metrics. There's deployment plugins that can deploy these to different platforms and so on. So we've extended this to support language models and some of the common frameworks for working within them. And basically, you get kind of a way of wrapping something that can be a call to OpenAI, or a call to a Hugging Face model that you build, or a custom one in PyTorch, or even a pipeline with LangChain or some custom function. And then you get this common interface. Like after you wrap this up, people can use it in an app using these standard functions like predict or deploy or evaluate without having to know the details. So very powerful for swapping them out. Another thing that you get from this as soon as you use it is MLflow will also automatically track information about each model. Like, for example, we track its model card at the time you downloaded it from Hugging Face, and other things about it, like the components of a chain in LangChain and stuff like that. And basically, you can, if you just import the MLflow libraries and call operations like log model for your model, you'll get all this information. And at the end, you'll get this common interface to the model, like just model.predict. So basically, as you write your code, you can automatically capture this information. And once you capture it, you also get a uniform interface for comparing the models. So this one actually just launched today. If you look at the MLflow website, there's a MLflow 2.4 release. And one of the things in it is a comparison view for, large, like sort of generative outputs like text. So for example, here we have DALL-E, which is a, open source model like you can run yourself on Hugging Face, and then GPT-4 and 3.5. And we have some data set of newspaper articles, and we ask them to summarize it. And you get this nice kind of view where you can summarize them. You can also download this as a table and search it and do other things with it. So these are, some basics that help a lot to have a workflow that's agnostic to the details of your implementation. The other part of it that I mentioned is evaluation. So we've got this evaluate function that has a lot of built-in metrics. It's very easy to extend with custom ones as well. And again, it like decouples it from the implementation of your model. And then the final one is monitoring data. Once you deploy something, again, super important. We found in our internal apps and with customers that like the sooner you can collect feedback and put it into your process, the better you can make your model. And with MLflow, we actually support a variety of deployment tools, many of which have powerful monitoring capabilities. Like for example, if you use Databricks, you just get back all your inferences as a table, and you can just run an arbitrary expression over it to set up an alert or monitor it that way. So that's just kind of the basics. I think it's very important to get your standard sort of ops processes into an LLM application if you want to go beyond the demo to something that's reliable, 90 or 95 or whatever, 99% of the time. We've been producing a lot of other resources about this if you want to check them out. One of the biggest things we've been building is support for QA kind of applications over a collection of documents. And we have a bunch of like reference applications. And actually, if you go to our website for Databricks docs, you'll notice there is a QA bot on there too. That includes like a vector database and post-processing of the outputs and guarding against bad questions so it doesn't start ranting about like a political topic and all the kind of stuff you need in this thing. And we're also running an edX course that's like completely free. That's about some of these ideas and all the peripheral things you can combine with language models. So definitely check that out. That just launched today, I believe. Okay, so that's kind of the basics, but what will programming with LLMs sort of look like in the future? I think it's still very, kind of wide open what the best way to program with these is. And today, people are building very cool applications, but it is still error prone. If people said machine learning was the high interest credit card of technical debt, that's one of the papers from Google, then prompt engineering is like sort of the payday loan of technical debt. Like it's, it'll work, but you may soon regret, all the stuff you did there to get your application working. So this is one of the problems we're trying to tackle in DSP, this programming model for foundation models more generally, especially language-oriented ones, from my research group. So the place we're coming from here is there are so many foundation models out there and so many ways of using them. So obviously there are large language models. There are so many techniques for getting them to produce answers that you want to try around. Not to mention you can train and fine tune your own. But there are also retrieval models. These are really critical to connect to a knowledge base. So we've invested a lot in those. Task-specific models, and also models for other types of data that you might want to combine. And as a result of that, a lot of people want to program and deploy pipelines of foundation models. And there's a lot of success for this in the literature, actually, in research and in real applications, as you can see from the success of things like LangChain. So I put in a couple of papers on the right, including Baleen, which is a multi-hop question answering paper that that we wrote that does repeated searches and knowledge gathering to answer a complicated question. But there are many more of them. So in general, building a pipeline of these seems like a great idea, right? You break down your problem into smaller subtasks, and then you've got these powerful models for each task. But the challenge is, once you've done that, it can be hard to figure out how to connect and optimize all the pieces of a pipeline. You can put them together, but what's the best way? Like, what's the best format to get data out of this one into the next one? How do you optimize them? And once you've set up this pipeline, every change to the pipeline essentially defines a new task. And if you want to fine tune one of the steps, you need to do it with data specific to what came from above it in the pipeline. So you've got, as you change your pipeline, there are so many different like ML training problems you have to run if you want to optimize it and get the best performance. So it's quite time consuming to really take one of these pipelines and make it very high quality. And we want to move developers very far away from that so they don't have to think about it. They don't have to like refactor a lot of code, for example, to switch between few-shot prompting and fine-tuning. They don't have to do anything very complicated to switch, between GPT 3.5 and 4 and stuff like that. So how do we do that? So we've created this programming model, DSP, which stands for Demonstrate, Search, and Predict, for foundation model pipelines. And the idea is pretty simple. Think of something like PyTorch, where you compose together, layers or operators. But here, instead of the layers being these like numerical, operators, they're foundation models, like a call to a language model or a call to a retriever, which is basically a search function. And instead of passing tensors between them, they're passing text, basically, or like objects with multiple, sort of text fields. Okay, so that sounds pretty straightforward. But it turns out if you set us up the right way, you can do a lot of stuff automatically for the developer. So inside DSP, there are basically primitives for three types of concerns. There's demonstrate, which is you tell us what you want, the behavior of your app to be, maybe with some examples. There's search, which is figuring out how to break down the problem, how to choose techniques for each step, and how to look for information in external systems. And there's predict, which is gathering, once you've gathered some information, how do you give your final answer out? And unlike something like LangChain, where like you have to hook together and pick a technique for each step, in DSP we've designed it so you just tell us declaratively what you want, the output to look like, and what are some good examples or data sets, and then the runtime automatically figures out how to optimize each step of the pipeline and co-optimize them together to get it to do that thing for you. So let me just show this with a simple example, which is a multi-hop search thing. So this is something we developed, a whole paper on how to do this at NeurIPS like a couple of years ago that, was able to answer these complicated questions using multiple searches over Wikipedia. So you could have, very complicated question that requires someone to do a little bit of research, look at many Wikipedia pages, follow the links to get an answer. And, we had a whole paper that kind of built this from scratch. Now, in DSP, you can write this pipeline very easily. So the input to this, maybe it's easier to start at the bottom. Basically, we'll start with this example object that has a question. For example, when was the creator of Hadoop given an award? Now, unless Hadoop is a piece of software. Now, unless you happen to know a lot about Hadoop, like to answer this question, you'd first have to figure out maybe what is Hadoop, who created it, what awards, if any, did that person get? So you have to do a little bit of research. And the strategy in Baleen is very simple at a high level. Basically, we'll get this example, and we have a max number of hops that we do, and we're going to we're going to call this question to query, basically language model call, where we say, hey, given this question, give me a search query I should run over Wikipedia. Then we retrieve, those outputs. Then we'll tell it, hey, now summarize, given my question and all the stuff I read on Wikipedia, what are some facts you took away from that? So again, passages to summary, sort of think of it as a prompt for doing that. And you just keep doing this a bunch of times to gather information. And then you finally say, hey, given the question and all the context, what is my answer? So how would this actually be implemented? So let me start actually by showing what these items look like, the question to answer. So this is something that we call the signature in DSP. Basically, we don't want people to write down a prompt with like lots of words and like, pretend you're a scientist or whatever. We just want them to tell us basically the signature of each step. So in here, and you can define every element of the signature. Think of this as a data type. You can actually kind of say what it is in natural language, and that will provide a hint to the model. So for example, here we say we'll have a context, which is sources that may contain facts, and a question to be answered, and the answer that we want is a short sentence, and we want the signature that goes from a context and question to an answer. Now, what happens if I actually run this program in DSP? So by default, if you run it, we have a way of generating a prompt to a language model that puts all these answers in and does a pretty decent job of actually getting it to do it. So imagine that in here, like we ran this and it actually found a couple of articles about Hadoop and Doug Cutting, and it asked the right questions. You'd end up with a context that's a few of these articles. You'd get this question. We actually automatically tell it to do chain of thought, and then it'll have an answer, which happens to be correct here. And we can optimize this prompt in the framework, and all users will benefit, without having to change their app. So we've separated sort of the prompt engineering from your spec of your app. But the even cooler thing that you can do in DSP is called dsp.compile, where you can give it a few examples. Actually, even like 10 or 20 labeled examples are pretty good. And then it will actually automatically run through them, figure out, what's the best way to do each hop. Like, for example, figure out for question to query, what kind of questions that I can ask would lead me to find the correct answer later. And then it will automatically generate a few shot prompt. So in this case, it will say, hey, here are a few examples of how I've answered multi-hop questions before. And the developer doesn't have to fill these in. We'll just do a search and find examples that work. And now I've got a new question, and can you answer it? So that basically automatically does few shot prompting and prompt selection for you. And even better, if you have a lot of examples, you can even train a supervised model for it. So this is sort of the idea at separating these two. It might seem a little bit crazy to try to just take prompt engineering and fine-tuning out of the hands of the programmer, but it actually works quite well in our experience so far. And this gives you a model a programming model that is very iterative. It's very easy to get started, and then you can collect data and make your program better. It's highly modular. We can do engineering in the DSP framework, and like all apps benefit from it without requiring everyone to migrate over. And it opens a huge number of optimizations. We're exploring a whole bunch of techniques, and we can try them all in your app and figure out which one works best. This is just an example of a task. This is this multi-step question answering task. And basically, a program like the one I showed you before is the state of the art across many data sets for few shot, basically solutions to this task, right? If you're not going to fine tune. And if you tell DSP to fine tune, then it's also very good at fine tuning compared to other ones. And one question we always get is, how does it just compare to like agents and LangChain? So these things here are the implementation using agents. You can see their scores on these benchmarks. It's like 34, 35. And the DSP one does a lot better because of this self-optimization based on data. So that's DSP. It's open source. You should definitely check it out. There's a really great getting started example. And there are many other techniques in this space that are powerful. I just listed a few on there. You may want to know. There are really cool techniques for like forcing the model to give output in a specific format, like guardrails. And LMQL. We have a project on LLM cascades where like we can use cheap models for easy questions, or we can ensemble multiple models to do better than any individual ones. There are also really nice post-processing tools, and you should definitely know about these if you're building these apps. But even better, I hope that in the future you don't need to know about them, and they can be done automatically in a framework like DSP. So that's what I wanted to show. Happy to answer a few questions if we got time.
We do. Thank you so much, Matei. Lots of ground covered, but lots of exciting things that you're working on that you highlighted. So thank you. We do have a question from the audience that maybe we'll start with. I think this is referencing your first set of slides where they're asking, what is the path to fix the confidence level for wrong answers? I think they're talking about like, how do you calibrate large language models in general, maybe?
Yeah, that's a great question. Yeah, so I think there are various ways to do this. So and I think from an engineering standpoint, like if you just want to get stuff done, you need you need to figure out like what do you need in your application and what's the best way to get there. So like I think a pure like ML person would say, well, like read a lot of research papers and like learn how to make your model produce confidence scores and all that stuff, which is great, and it's awesome that people are doing it, and I'm sure it'll get better. At the same time, though, if you're just trying to get stuff done, like one really powerful technique is combining your model with a retrieval system if it's searching over a knowledge base, or like all the knowledge is good, and basically telling it you have to provide an answer that's in there, or even checking after, right? Like saying, hey, the model produced this paragraph. for each sentence, like, is this supported by the document? So this works pretty well. Some things can still get through in this. So another technique that works well and is a bit more limiting is actually what's called extractive generation or question answering. So extractive is you don't tell it like go generate whatever you want. You tell it like either return a substring of this paragraph that we found, or maybe select here are a few paragraphs, grab some of them and summarize them. But so basically there's a spectrum between like the freedom of generation you give it versus how much you force it to be grounded in stuff that you know is true. Yeah.
Makes sense. Thank you. And then one last question maybe, which is, I think really exciting work around Dolly that got people really excited, and you created your own data set of this instruction tuning data set by using Databricks employees, and you're talking about how hard it is to come up with 13,000 unique prompts and stuff. So given that it's a data-centric AI conference, could you talk about some of the challenges in building this data set or considerations that you'd like to highlight? Yeah,
that's an awesome question. Yeah, I don't know if everyone knows about this. So we saw, there were all these results that said if you have examples of like, chat assistant conversations, if you have like 50,000 examples from Stanford Alpaca and like other groups, you can actually fine tune like many language models to become very good at conversation, which was very surprising that you could do it with tiny models. But there were no commercially usable data sets because OpenAI says you can't use their output to compete against them. So, so everyone was doing it with that in research. So we had a bunch of employees and we said, hey, can we just get our employees to create some chats? It's hard though, because we did not want them to copy stuff from the web. We don't have copyright to, and we wanted to get long form answers. So the first time we tried it, we just said, put in a thing, prefer long form answers. It wasn't great. Everyone was asking very similar things. People were still copying, from like whatever Stack Overflow or stuff like that. So it actually didn't work well. It led to some instruction following behavior, but not much. So we actually came up with a technique to get good stuff, get good answers, which is we had like 7 categories of questions, and we had a separate sort of process for each one, and we had a way to use existing content that we know is open to generate it. So for example, one thing we wanted the task of like you ask a question and it answers in a paragraph. But how do you get like questions on diverse topics, and how do you get good paragraphs? So we told people, go to wikipedia.com/random, puts you on a random page. That content is commercially usable. That's the whole point of Wikipedia. It's open. And just take the first couple of paragraphs, or take a random paragraph, and then ask a question about it. And we're going to use your question that you typed as a human as sort of the input, and the Wikipedia paragraph as the output. So we guarantee we get a good paragraph. We guarantee we get diversity from the randomness. So we had a few other tricks like that. Actually, we want to write up a little bit about them that led to a pretty nice data set.
That's very interesting. So it's not like that you provided the questions and you had people write the answers. It's like you took the answers and then had people write the questions.
Yeah, that one was like, in others we did it the other way, but the hardest thing is to get long form answers, because people are sitting there, they don't have a lot of time, they get bored, and not everyone's good at writing long form stuff. So anything you can do to like flip the problem around, and also to force diversity, like this /random thing, helped. Yeah,
that's awesome. And I guess like even if you ask people to write the answers, a lot of people probably nowadays would go to ChatGPT and get the answer.
Yeah, and we wanted to avoid that. We were very clear, we sent lots of emails in all caps. People were still doing it. So, but then we figured out like a way to do all these tasks that don't have that problem. Yeah,
that makes sense. Well, thank you so much for taking the questions and for the amazing talk, Matei.